Welcome to The Explainer. We're diving deep into the state of quantum gravity as of 2026. And believe me, the search for a final theory has been completely turned on its head.
Okay, let's just jump right in. For decades, the holy grail of physics was finding that one beautiful theory to explain everything. But that's not the game anymore. The quest has a new map, a new philosophy, and a very, very different destination.
So, things have totally flipped. Physicists now think that almost all of the theories that look great on paper, the ones that are mathematically perfect, are actually physically impossible. And that's led to a completely new strategy. Instead of trying to find the one needle in the haystack, the goal now is to just burn the haystack down, eliminate all the wrong answers. So get this. Some of the smartest theoretical physicists on the planet have become explorers, cartographers, really. But they're not mapping new continents. No, they're charting the enormous, forbidden territory of what can never exist.
First up, let's talk about what's actually possible. They call it the landscape. Think of it as the complete collection of every possible universe that string theory says could exist. And the number of possibilities? Well, it's just insane. It's a 1 with 500 zeros after it. Our universe, everything we see and know, is just one tiny, tiny little island in that cosmic ocean.
But then, surrounding that tiny island is something way, way bigger, the swampland. This is basically a graveyard for theories. They look good, they seem to make sense, no obvious problems, but they have a fatal flaw buried deep inside. They just don't work with quantum gravity. They're cosmic dead ends.
This, right here, this is the new mission. The job of a physicist trying to solve quantum gravity is to draw a bright, sharp line in the cosmic sand. On one side, you have the landscape, where our universe has to be, and on the other, the forbidden swampland of impossible realities.
So how do you even begin to draw that line? Well, they've come up with a set of rules, or conjectures, that act like cosmic bouncers at the door of reality. Take the weak gravity conjecture. It's a really simple but powerful idea. In any universe that can actually exist, gravity has to be the weakest force. So if you come up with a theory where gravity is stronger than, say, electromagnetism, nope, you're out. Your theory gets tossed straight into the swampland. Okay, but here's where it gets really interesting. Not everyone agrees on how to draw this map. You've got these rival teams, different schools of thought, all using their own unique tools and ideas to figure out what reality is actually made of. So, on one side, you've got string theory, taking this top-down approach. It starts big, with like 10 dimensions, and tries to boil it down to the 4 we actually experience. But its main rival, loop quantum gravity, does the complete opposite. It's bottom-up. It builds space-time piece by piece from these tiny, unbreakable loops. It's kind of like the difference between a smooth movie reel and a digital screen made of individual pixels. And loop quantum gravity isn't just a vague idea, They're getting super specific. As of 2026, researchers have calculated what they think is a fundamental constant of space-time itself. The idea is that if you could zoom in to the absolute smallest scale, reality isn't smooth at all. It's a grid, a crystal structure with a fixed spacing of about 2.7 times the Planck length, which is the smallest possible distance in our universe. And then you've got the real radicals. These guys are saying, what if gravity isn't fundamental at all? Their idea is that gravity is an emergent thing, something that just sort of arises from deeper rules about information and randomness. It's like how temperature isn't a fundamental thing. It just emerges from the jiggling of a bunch of atoms. And this isn't just some philosophical coffee shop talk. When they tested this emergent gravity idea against the movement of dwarf galaxies, it fit the data with a 5.2 sigma preference. Now, for anyone who follows the stuff, you know that 5 sigma is the gold standard for a discovery. This is a seriously tantalizing piece of evidence that they might really be onto something. So let's go back to that number from before, 10 to the 500 possibilities in the landscape. That number is just, it's so big, it's meaningless to us. There's no way a human brain, or even all the human brains on Earth, could ever hope to explore that space. So what do you do when you have a problem that big? You call in a new kind of explorer, artificial intelligence. As you can see here, they're using all kinds of AI for the job. They're taking AI that's good at recognizing faces and training it to classify the incredibly complex shapes in string theory. And it's working. It's finding promising little neighborhoods in that impossibly vast landscape that might just look like our own universe. All right, but this all leads to the billion-dollar question, right?
Are these just really beautiful, elegant ideas stuck on blackboards and in supercomputers? Or can we actually see any of this stuff out there in the real world? Well, the hunt is on. Scientists are basically cosmic detectives now, looking for these tiny little fingerprints of quantum gravity. They're hoping a new space mission called LISA might hear this faint background hum of gravitational waves from the Big Bang. Or they're scouring the afterglow of creation for any little anomaly that doesn't quite fit. And in late 2025, they found something really remarkable. They looked at light from the very early universe and found that it had been twisted. Just a tiny bit, about 0.3 degrees. As this ancient light traveled across the cosmos for billions of years, something twisted its polarization.
And this is huge. Why? Because this weird little twist is exactly the kind of thing that some string theory models predict should happen. Now, it's not a smoking gun. Not yet. But it might just be the very first crack in the wall between these incredibly abstract theories and cold, hard, observable fact.
But all this excitement, this frantic search for clues, it's all happening during a pretty intense, pretty heated time for the physics community. This long, long wait for experimental proof has really created some tension. And this quote, this really gets to the heart of the debate. The critique is powerful. If a theory doesn't make predictions you can actually go out and test, is it even science anymore? Or has it become something else? This has kicked off a real theory crisis about what progress in physics even looks like anymore. And this isn't just talk. You can actually see the response in the money. The big funding agencies are now going out of their way to support projects that build a bridge between the super abstract theory and stuff we can actually build and test in a lab, especially ideas from the world of quantum computing. So here's the really wild part. All these different roads we've talked about, string theory, loop quantum gravity, this emergent gravity idea, they all seem to be leading to the same mind-blowing destination. They're all pointing to this idea that gravity, quantum mechanics, and information, they aren't separate things. They're all one. And that space-time itself isn't the stage for the show, it's woven from the show, created out of the connections of quantum entanglement. And that leaves us with this final incredible question that's going to drive physics for the next generation. Are we explorers, mapping a reality that's already out there, like charting a new continent? Or are we more like code breakers, trying to figure out the fundamental logic, the source code, that's literally processing the cosmos into existence around us? The answer, whatever it is going to change everything.